The glitch is real. Why physics says time is breaking down. The second didn't land. Two atomic clocks, phase-locked for years, slipped by a hair during a solar storm. One heartbeat of time scattering into noise. Engineers stared at the trace where the tick should have been and found a smear. If seconds can smear, GPS veers, trades misfire, grids wobble. We're not chasing magic. We're following anomalies that behave like processing limits. Deja vu clusters, cosmic ray bit flips, the Muon strange wobble, the Hubble Rift, threads that tug in one direction. What if the universe runs on a finite information and energy budget? To see why a second can slip, we need the first cracks. The first cracks, human-scale glitches. Start small, inside your head. Deja vu feels like time stuttering, a hallway you've never walked looping on itself. Neuroscience points to memory pathways misfiring. Recognition signals arriving a fraction before perception, so the present gets tagged seen already. Under stress, your internal metronome drifts. Microsaccades reset visual input. Attention blinks leave gaps that your brain autofills. You don't notice the edits, just the eerie aftertaste of repetition. Most of this is reproducible in labs. Tug a circuit here, delay a signal there, and the mind renders continuity from incomplete frames. Now step outside the skull. A pilot on a high-latitude route during a solar storm taps the chronograph and frowns. The cockpit clock disagrees with the flight management system by tiny milliseconds. Then the gap closes, then opens again. Later, the data logs show nothing catastrophic, just a brief storm of corrections, while the memory of that wobbly second sticks like grit in the teeth. Pilots are trained to trust instruments over feelings. But the feeling matters. It's the human sensor noticing when rhythm slips. Meanwhile, something else is happening in the metal. Cosmic rays, high-energy particles from space, punch through our chips and flip bits. No scorch marks, no broken board, just a 0 becoming a 1 at the wrong time. In aerospace and data centers, these soft errors are documented. EC to memory catches many, some sneak through. A voting machine adds a phantom vote. A plane's avionics throw a nonsense warning. A cryptocurrency wallet's key index misaligns by 1 and triggers a cascade. Not a ghost in the machine, just the universe tapping the hardware, reminding us every calculation rides on physical stuff. Software treats time like a clean integer until it doesn't. The year 2038 problem sits there like an unexploded shell. 32-bit signed second since 1970, rolling over into nonsense. We've known for decades. Patches spread, then miss a corner case in some industrial controller that'll be forgotten until it fails at 3:14 a.m. Then there are leap seconds, the efforts to keep atomic time in lockstep with Earth's slowing spin. Insert 1 extra second and watch stacks freeze, schedulers spin, databases double insert, entire services stall because a single tick arrived twice. Time isn't free, it's bookkeeping, and bookkeeping costs compound. Here's where it gets crazy. Humans are lenient with time. Machines are not. Your brain smooths over a skipped frame. A consensus algorithm demands exact order. Financial exchanges now carve time into nanosecond slices, racing light across microwave links. When a GPS satellite's clock drifts, corrections rip through the chain. Phones, towers, trades, position fixes. We built civilization on synchronized seconds, and the tolerance keeps shrinking. The more we compress the buffer, the less room there is for correction. What nobody knew at the time of that cockpit twinge, the same storms that nudge clocks also load the global error budget. In high latitudes, the ionosphere swells and crackles, signals bend and slow. GPS receivers juggle correction models while cosmic noise surges. Each layer compensates for the one beneath, and sometimes compensation arrives a tick late. The fix works, until it doesn't. Consider attention resets again. In crowded, fast-moving scenes, the brain prioritizes change and drops the rest. Engineers do the same. Rate limit logs, sample metrics, approximate to keep the dashboard readable. It works, until an outlier hides between samples and grows teeth. Power grids know this intimately. A relay misses a beat, a protective scheme misreads phase, and suddenly operators are chasing timing ghosts across states. A second stretches when decisions matter because our bodies overclock. Adrenaline widens the aperture, but the world's second stays the same. Or does it? In high-demand systems, the effective second thickens with retries, checks, and rollbacks, computation paying interest on its own uncertainty. Let's talk about the small personal glitch. A programmer stares at a postmortem from a leap-second night. The fix was simple: smear the extra second across a minute. Yet one service didn't adopt the smear. It jumped. Another assumed monotonic time and looped back into the past, waiting for a timestamp that would never arrive. The system didn't die. It thrashed until operators drained traffic and restarted demons. No villain. Just the price of assuming time is a straight, uniform line in a world that sometimes inserts a comma. Meanwhile, across town, a hospital's monitoring system catches a cluster of false alarms. Later, investigators trace it to a firmware update interacting with a rare cosmic ray burst during a geomagnetic blip. Nobody was harmed. But the log shows dozens of bit flips in a narrow window. The team adds redundancy, spreads the load, widens the margin. Every fix burns energy, complexity, and human attention. This is the quiet economy of time. Keep it smooth, spend more. There's also the uncanny clustering of déjà vu. Not proof of anything cosmic, but the statistics are odd. After major stressors, storms, blackouts, global events, self-reports spike. Maybe it's anxiety, maybe it's sampling bias, or maybe the brain's predictive machinery strains when the world jitters, surfacing the feeling that the frame repeated. The lab doesn't claim a glitch in reality. It doesn't need to. It shows how closely our sense of time is tied to error correction. Here's the point. We keep adding layers of protection: ECC memory, smearing algorithms, monotonic clocks, consensus protocols, and still live with residual stutter. The stutter is small. It's also stubborn. You can feel it in a cockpit during a solar storm. You can read it in a postmortem after a leap second. You can measure it in a SRAM cell struck by a particle born in a galaxy you'll never see. While humans mistime reality, physics records stricter contradictions. If these are the first cracks, where do the seams show up when we zoom out? Cosmic budget warnings, the finite information universe. To see the seams, follow the receipts. Start with the Bekenstein bound. Take any region, say a sphere you could cut between your hands. There's a maximum number of bits you can store inside it, and that cap scales with the surface area, not the volume. That's backwards from intuition. Instead, nature says the boundary holds the ledger. Pack more stuff in, you expect storage to scale, like the space you fill. Push past that, and gravity answers with collapse. What nobody knew at first was how deep that limit runs. Black hole thermodynamics took the hint and wrote it in heat. A black hole's entropy tracks the area of its event horizon. The more area, the more microstates. An accounting of how many ways the inside can be arranged while the outside looks the same. Temperature, entropy, energy. The words of thermodynamics suddenly speak about geometry. It's a bill written on the skin of space-time. Now fold in Landauer's Principle, erasing a single bit, resetting a memory cell from we don't know to we know, costs a minimum amount of energy as heat. It isn't a metaphor. You can measure it in careful experiments. Push computation, burn energy. Compress state, generate heat. If the universe is doing any bookkeeping, tracking fields, interactions, histories, it's paying with energy to keep the record tidy. Meanwhile, the holographic principle steps out from the chalkboards. If the maximum information in a volume scales with its surface, maybe the entire 3D world is describable by data living on a 2D boundary. Not as a cheap trick, but as an economy. No more bits than necessary, encoded redundantly to keep errors in check. Compression, not opulence. The bulk can look continuous, while the boundary enforces the budget. Here's why this matters. If memory is capped and erasure costs heat, then shortcuts aren't scandalous. They're survival. You don't render every leaf in high resolution if the viewer can't see it. You don't recompute a state if you cached it safely. Physics doesn't say the universe is cutting corners. It says the rules favor efficient descriptions. That's different from fake. It's a finite system leaning on structure. Black holes sharpen the point. Throw in a library, a planet, a star. Outside, you only track mass, charge, spin. The horizon inflates to match the entropy, then radiates away information as Hawking radiation over absurd timescales. If erasure has a cost, black holes are the ultimate payers, slowly returning information to the universe as thin, cold light. The process is slow because the bill is large. So where will we see a budget in action? In places where the ledger runs tight. Think about error correction in quantum systems. Entanglement doesn't allow messages to outrun light, but it shares correlations like a global state that has to stay consistent. Maintaining that consistency across separated parts might be cheaper than recomputing everything locally. Cache coherency without the wires. It's a story about cost, not about cheating. Zoom out. Cosmology sets an information horizon. There's only so much universe we can interact with, so only so much information we can meaningfully store about. The cosmic microwave background, the cooled afterglow of the early universe, carries a finite number of modes. When we estimate parameters from it, we're scraping the barrel of available bits. Precision is constrained by the number of independent samples the sky allows. Meanwhile, every measurement is a tiny entropy negotiation. You cool a detector, isolate it, reduce noise, and in exchange, you burn energy elsewhere to maintain the low entropy pocket. The cleaner the bit you want, the more you pay. Data centers feel this viscerally. Move a petabyte, pay the power bill, delete a petabyte, pay it again. The physics scales up neatly because it's the same accounting everywhere. If that's the economy, seams should look like trade-offs. More detail here, less refresh there. High fidelity constants, but occasional tension in derived quantities. Systems that preserve global consistency by smoothing over local roughness. To be clear, this isn't proof of a simulation. It's a way to read recurring patterns, limits that bite at boundaries, prices paid in heat when logic flips, precision bought at the cost of time. And there's the quiet threat. A finite memory universe doesn't break. It prioritizes, it compresses, it encodes redundantly. When stress rises, more states to track, more correlations to maintain, it can respond by stretching the rendering interval. The second feels thicker where retries pile up, while somewhere else the budget tightens. We don't need to imagine a cosmic processor throttling. We can watch physics prefer cheaper paths. This was the moment everything changed in our thinking. Anomalies stop looking like magic tricks and start reading like overdrawn accounts. A bound on information here, a heat cost there, and suddenly a wobble isn't a scandal, it's a receipt. If memory is capped, where do we see the seams? Follow the universal clocks that won't agree and the tiny particles that won't settle. The ledger is about to show its first big mismatch. The Hubble Rift. 2 clocks, 1 universe. 2 clocks are arguing across the sky. One is the early universe clock, read from the faint static of the cosmic microwave background, the afterglow mapped with Planck satellites and ground arrays. The other is the late universe clock, built from exploding stars, lens galaxies, and calibrated distance ladders. They're both precise. They won't agree on how fast space is expanding right now. Start with the early clock. Planck measures tiny temperature ripples frozen when the universe was hot and dense. Feed those ripples into a well-tested model. Dark matter scaffolding, dark energy pushing, normal matter glowing, and you get a tight prediction for the Hubble constant. It's careful, global, averaged over the whole sky. That clock says today's expansion rate should land at 1 number. Meanwhile, across town in astrophysics, the distance ladder crew does it differently. They build a chain. In our cosmic backyard, parallax gives hard distances to nearby stars. Those stars calibrate Cepheid variables, pulsing beacons in other galaxies. Cepheids calibrate type Ia supernovae, standardizable candles bright enough to see far out. Stack the rungs, measure redshifts, and you get a direct local expansion rate. That clock lands higher. The 2 error bars used to overlap. They don't now. Why it matters isn't a pedantic constant fight. Expansion sets the scale for time and distance in cosmology. It decides how old the universe is, how structure grew, how galaxies assembled, and how dark energy behaves. If the clocks won't sync, either something subtle contaminates a measurement, or the model tying early ripples to today's pace is missing a piece. Both options carry a price. Here's the human version. Imagine groups that have spent a decade shaving uncertainties, building better detectors, revising calibrations, arguing with their own data until the numbers hold still. Careers hang on those decimal places, funding bets on them. Conferences turn into careful cross exams. Nobody wants a phantom. Nobody wants a fudge factor. They want the tick to land. Call it a desync. The early clock is like a timestamp logged at universe boot, extrapolated forward through the rules. The late clock is a timestamp stamped on today's screen, averaged over countless local patches. If the rules are perfect and the bookkeeping is clean, they should match when you account for noise. They don't. The mismatch has persisted through new instruments, alternative candles, and revised priors. What nobody knew at first was how sticky the rift would be. Blame shifts. Maybe Cepheids are trickier than we thought. Dust, metallicity, selection bias. Teams swap to other rungs, tip of the red giant branch, masers, time delay lenses, and still find high values. Maybe Planck's inference depends on the assumed recipe of the early universe. People try tweaks, extra relativistic species, early dark energy, sterile neutrinos, changes to recombination. Some soften the rift, most
create tension elsewhere.
Fix the early clock, rip the stitching on nucleosynthesis. Fix the late clock, break large-scale structure growth. This is where the budget theme peeks through. Two ways of telling time. Global compression of ancient information versus local high-fidelity snapshots are returning different answers. If the universe prioritizes consistency under finite information, there's a trade-off hiding here. The early universe read compresses everything into a few parameters with small errors. The late universe read gathers many heterogeneous samples with complex systematics. Each method spends its precision budget differently. The disagreement looks like the cost of reconciling two compressions. Meanwhile, instruments push harder. Supernova teams chase better zero points with space telescopes, avoiding atmosphere and dust. Planck's successors, ground-based CMB experiments, dig into polarization and small scales. Lensing surveys weigh the cosmic web. Radio arrays time pulsars to build a gravitational wave background clock. The more clocks we set, the more we expect convergence. The irony is, we're now precise enough to force a choice: new physics or a subtle global error. Here's a micro story. A grad student spends nights aligning supernova light curves, watching the stretch and color corrections snap into place. She moves one calibration star from the sample and the Hubble value shifts by a whisper. She moves it back. The whisper returns. It's not enough to save the truce. In another building, a theorist adds an early dark energy term that briefly accelerates expansion before recombination. The early clock ticks faster for a moment. The late reading relaxes toward it. But the change drags on other data like a snag on a sweater. While that's happening, statisticians comb for human bias. Are teams unconsciously herding toward their priors? Blind analyses help. Pipelines hide the answer until methods are locked. Results still split. The rift resists personality in pipeline. It starts to feel like a real seam. There's a quiet psychological cost. If the second you trust is defined by models, and those models disagree across epochs, confidence thins. You still fly satellites, still map galaxies, still calculate orbits, but a question hums beneath the calculations. Which clock are we living on? Framed this way, the Hubble Rift is a global version of clock drift, a universe-scale desync between two impeccable metronomes. It doesn't mean the system's failing. It means we're at the edge of a budget where assumptions matter. Either the rulebook needs an extra page, or one of the clocks is reading through glass we haven't cleaned yet. And when you zoom smaller, the timing cracks whistle. Muon G-2, the particle that won't behave. Shrink the frame from galaxies to a single particle that lives for 2 microseconds and still manages to throw shade at our rulebook. The muon is a heavier cousin of the electron. Same charge, same spin, just bulked up. Put a bunch of muons in a magnetic field and they precess. Their little internal magnet wobbles like a spinning top. The rate of that wobble is g. In a perfect interaction-free world, g would be 2. Quantum fields crowd the scene, so the true number is G2, a small deviation that encodes everything the muon feels from the vacuum. Here's why this matters. That tiny wobble is a referendum on the standard model, our best set of rules for particles and forces. If G2 lines up with predictions, the book holds. If it doesn't, something unseen is tugging on the muon. New fields, new particles, or a flaw in how we're summing known effects. The stakes aren't abstract. Every proton in your body is accounted for by that same framework. If the rulebook bends here, everything compiled from it inherits bugs. The human moment is late nights at Fermilab, a ring the size of a skating rink, humming with magnets, and teams timing decays down to nanoseconds. They inject polarized muons, watch them orbit, and count the electrons that spray out when muons decay, because the direction of those electrons tracks the muon's spin. The frequency they extract is the wobble. An anomaly pinned to the 4th decimal place means months of calibrations, alignment, field maps, and cross-checks. You don't get to cry new physics because a cable was loose. Meanwhile, theorists fill blackboards with the contributions that add up to the prediction. Quantum electrodynamics piles on precise terms, photons flitting in and out of existence. The weak force adds its whisper. Then come hadronic effects. Quark-antiquark pairs bubbling in the vacuum, gluons tangling, the murky domain where QCD's grip is strong and calculations get hard. You can estimate those hadronic terms 2 ways. Use data from electron-positron collisions to feed a dispersion relation, or simulate QCD on a lattice with supercomputers. For years, the best consensus leaned on E plus E minor data. The old story from Brookhaven was a hint. The measured G2 was higher than the standard model prediction, a few sigma off. Not a discovery, but a nudge. Fermilab rebuilt the experiment, moved the Brookhaven ring, and pushed uncertainties down. Their first and second runs strengthened the tension with that E plus E minus base theory. The wobble refused to settle. Press headlines flirted with cracking physics. Inside the field, nobody popped champagne. They tightened bolts. Then theory moved. Lattice QCD calculations matured, and in some results, pushed the predicted G2 closer to the experimental value, shrinking the gap. That sounds like a rescue, but it shifted stress onto other observables. Hadronic vacuum polarization influences not just G2, but also how the fine structure constant threads through other precision tests. Make G2 happy with lattice, and you might upset E plus E, minor cross sections, or electroweak fits. Fix a tick here, stretch the ledger there. It's a familiar theme: budgets and trade-offs. This was the moment everything changed in tone. The anomaly wasn't a clean banner for new physics, but it wasn't dissolving either. Instead, it became a stress test for our entire modeling stack. Detectors, magnetic field uniformity, pileup corrections, beam dynamics, decay asymmetries, and on the other side, multi-loop QED, hadronic light-by-light scattering, data-driven integrals, lattice systematics. Every layer carried an error bar that had to be paid for. Here's a micro-story. An accelerator physicist sits with coffee gone cold, comparing two independent field maps of the storage ring. One map is based on trolley probes that ride inside the ring. The other relies on fixed probes stitched together with a model. The difference is tiny but correlated with temperature. They rerun the analysis with a corrected drift. The central value shifts by a hair. The uncertainty narrows. The headline number barely moves. The wobble is still obstinate. What nobody knew at the time of Brookhaven's first hint was how much the conversation would pivot to hadronic light-by-light scattering, a notoriously tricky contribution where three photons dance around a quark loop. Different modeling approaches give slightly different answers. Lattice is starting to weigh in. Each advance reduces wiggle room. If an unknown particle were boosting G2, it'd likely show up elsewhere. Rare decays, colliders, cosmology, the hunt widens, the cost climbs. So where's the seam? If you read G2 as a bill, it's a receipt for vacuum complexity. The muon's wobble integrates over everything that can couple to it, from the clean QED fringes to the messy hadronic soup. Our predictive power depends on how we compress that soup. Data-driven shortcuts versus first principles computation. The disagreement's persistence looks less like a magic trick and more like a budgeting problem. Precision spent unevenly across methods and measurements, and that ties back to time. These rings are clocks. The precession frequency is a timing signal born from quantum fields. When your clock won't align with theory's tick, you either miss the gear or there's a new cog in the machine. Labs keep refining the gear train, theorists keep redrawing the diagram. If the rulebook bends, the bend is small but consequential. A hairline that propagates. Bugs show up in networks too, at cosmic scales.
Fast radio bursts and rendering spikes. Now listen for the universe clearing its throat. In 2007, while combing old pulsar data, astronomers found a millisecond-long ping so bright it shouldn't exist. Then another. Fast radio bursts, FRBs, land like camera flashes from deep space. In a few milliseconds, they pour out more radio energy than the sun emits in days, then vanish. Some never repeat. Others stutter, then rest, then fire again. The sky is quiet until it isn't. Stakes first. When a burst hits, telescopes swing, pipelines trigger, and people sprint. The dispersion, the way higher radio frequencies arrive earlier than lower ones, acts like a yardstick for distance. The more the signal is stretched, the more plasma it crossed. Many FRBs look extragalactic, even intergalactic. That means the engine lives in extreme fields. Compact objects, magnetars, neutron star mergers, maybe exotic plasma shocks. It also means the event is brief yet information dense, an entire story told at once. Action is messy and thrilling. A burst pops in a survey instrument, say Kaime's Wide Field Radio Array, and software screams. Within seconds, automated alerts ripple across a network. Observatories in optical, X-ray, gamma rays, even neutrino detectors check their buffers. Did they see anything coincident? Sometimes a repeater gives mercy. It fires again. Teams triangulate with interferometers, nail a host galaxy, and zoom in on a star-forming knot. Magnetar flares become the leading suspect, especially after a galactic magnetar produced a FRB-like event. But there's variety.
Some bursts seem too bright, too structured, too patterned for a single template, like seeing multiple compression algorithms in one data stream. Here's where burstiness reads like load spikes. In computing, most of the time your system handles steady traffic. Then a surge hits, flash sale, breaking news, a bot swarm, and queues swell. You drop detail, buffer, or you fail. FRBs feel like cosmic queues emptying. A magnetar's crust cracks, magnetic fields reconnect, and energy that's been bottled in complicated twists seeks a cheap exit. The universe pays down stored complexity in a single clean blast. Compression in, sudden decompression out. Meanwhile, multi-messenger coordination is our stress test for reality's bandwidth. A gravitational wave alert from LIGO pings phones. Kilonova teams scramble telescopes before the glow fades. Neutrino detectors post a candidate. Gamma-ray satellites scan Earth's limb. For far Bs, the window is punishing, milliseconds, but repeaters buy time. When a repeater flares in a quasi-periodic way, scheduling locks in. Then the burst shows substructure. Microsecond spikes stacked in a drifting pattern like a chirped signal. Plasma lensing could explain it. So could emission regions sweeping across our line of sight. Either way, the data rate is insane. Instruments are pushed to dump buffers faster, clock stamps tighter, and still some frames smear. Impact lands in two places. First, astrophysics gets a new ruler. Average the dispersion across many FRBs, and you map the missing baryons in intergalactic space, the faint plasma that hides between galaxies. Second, we confront a cadence problem. Most of the universe is slow. Stars breathe in hours, galaxies evolve in eons. FRBs, pulsars, and magnetars jam speed into the timeline. They force us to sample fast without drowning in false positives. Every extra millisecond of timestamp fidelity costs hardware, power, storage, and attention. Our instruments become participants in the economy we're describing. Higher fidelity, higher price. Now keep the budget lens honest. FRBs aren't evidence of a simulation. They're likely magnetars and plasma doing hard, real work. But their rhythms hint at capacity edges. Repeating sources show activity windows, weeks of storms, months of silence. Some cluster near galactic centers, where magnetic fields and plasma density complicate propagation. The pattern looks like a system that accumulates stress, then vents quickly because slow leakage is expensive. That's not supernatural. It's efficient. Here's a micro-story. A night crew in British Columbia watches Chinese waterfall plots. A repeater they've nursed for a year erupts. 5 bursts in 10 minutes, each with different substructure. Slack channels fill. A VLBI network swings in. Timestamps align to microseconds. After dawn, the cross-correlation resolves a host dwarf galaxy with fierce star formation. The lead posts a plot. Arrival times versus frequency. A neat sweep. Someone jokes it's the universe zipping a file. Nobody laughs long. They're too busy tuning dead dispersion. What nobody knew at first was how FRBs would train us to think in buffers. You can't store everything, so you keep ring buffers hot and dump on trigger. You pre-compute dead dispersion trials. You chase latency out of the clock path. The telescope becomes a real-time decision engine, choosing which milliseconds to keep. That's the clue.
Programmer's dilemma written in sky noise, throughput versus fidelity. Keep more bursts with lower detail or fewer bursts with richer structure. Read the scene with the broader story. If bandwidth is finite, the universe may preload. Magnetars entangle energy in fields for years, then release it in ounces of time. Networks of observatories prime their buffers, then freeze frames on cue. The quiet nights aren't waste. They're the price of being ready when the spike hits. Interpret it carefully. FRBs point to a cosmos that prefers batching and bursts when the cost of continuous tracking runs high. If bandwidth is finite, the universe may preload scenes. Quantum shortcuts, entanglement, as non-local catching. We've been talking about bandwidth and budgets. Now, step into a lab where the universe seems to get a discount. 2 photons are born together, then fly apart. Measure one, you immediately learn something about the other. No signal crossed the gap. Nothing traveled faster than light, yet the results are correlated beyond what any local script could pre-write. That's entanglement. It doesn't send messages, it enforces consistency. Here's why this matters for our budget story. Bell tests took decades to close loopholes. Detector inefficiencies, timing windows, communication sneaks. Teams placed detectors in separate buildings, even separate islands,
choosing measurement settings with fast random number generators while the photons were mid-flight. The correlation still violated Bell inequalities. They didn't know each other's questions, but their answers locked together. It's as if the universe stored a shared state that both measurements read from, not a conversation afterward. Think of it as non-local caching. In computing, you can keep a shared piece of state in a cache so different processors see coherent results without recomputing. Entanglement looks like that, with rules. You can't use it to shout across space. You can't flip a bit over there by choosing a setting here. But when both sides query, the joint answers respect a global ledger. The cost is paid in preparation and isolation. Maintaining that shared state is fragile and expensive. Action looks like midnight optics. In a city lab, teams send entangled photons down fiber to 2 rooftops kilometers apart. Detectors click. Each side's polarizer angle changes on the fly, driven by high-speed randomness. The timestamps have to be tight, nanoseconds, and clocks must be disciplined to a common reference. Then they do the math. The violation appears, small error bars hugging the line. It's a quiet thrill, not a magic signal, a constraint. The universe refuses a local hidden variable story. It prefers one that keeps a global pattern intact. Teleportation adds a twist. You can take an unknown quantum state here, and, using an entangled pair and 2 classical bits, recreate that state there. Nothing physical travels except ordinary messages, yet the state reappears with fidelity set by the entanglement quality. It's not Star Trek. It's more like moving a file by sending a short diff, because both sides already share the big chunk. Pre-shared structure lowers the bandwidth of change. Entanglement swapping goes further. Entangle A with B and C with D. Measure B and C together the right way, and suddenly A and D, who never met, become entangled. The network gained a long-range correlation without ever touching the endpoints. That's a caching network, stitching coherence across distance by consuming local resources at the junction. Every swap spends a fragile commodity, clean entanglement. Noise eats it, heat eats it, time eats it. What nobody knew early on was how engineering this would feel. Quantum repeaters aim to build an internet of entangled links. They buffer entanglement in quantum memories, purify noisy pairs by sacrificing some to fix others, and coordinate classical signals to say, use this pair now. Every step adds latency. Every purification costs yield. It's a balance between fidelity and throughput, the same dilemma we've been tracking in telescopes and data centers. Meanwhile, the no signaling rule stands firm. You can't beat light. The shortcut isn't communication, it's consistency. From our lens, that's cheaper. Keeping a global constraint satisfied can be less costly than letting everything diverge and then reconciling. Think of accounting. Double entry keeps books balanced at every transaction, avoiding massive audits later. Entanglement feels like double entry physics. Here's a micro story. 2 groups coordinate an inner-city bell test using independent atomic clocks and GPS. A winter storm threatens fiber links. They switch to free space beams through clear air corridors. Temperature gradients jitter the path. Adaptive optics corrects the twinkle. The violation still posts. The relief isn't theatrical, it's practical. The consistency survived a hostile channel because the preparation was careful and the accounting was strict. Now zoom to theory.
Entanglement isn't a bonus feature. It's the glue of quantum mechanics. Many body systems use it to encode phases of matter. Error-correcting codes in quantum computing spread information across many qubits so local noise can be fixed without learning the message. Holography hints that space-time geometry itself could be sewn from entanglement patterns. In those models, connectivity, who's entangled with whom, shapes distance. The boundary code protects a bulk that emerges from relationships, not coordinates. Impact lands in 2 places. First, technology. Quantum key distribution, teleportation relays, sensor networks that beat classical limits. Each tool pays the same tax. Entanglement is hard to make, harder to keep. Second, interpretation. The universe appears to favor global bookkeeping over local narratives when budgets run tight. It won't let you exploit that to break causality, but it will use it to keep answers compatible. Read it with our thread. Local rendering versus global consistency is a trade-off. Entanglement looks like the universe pre-computing relationships, so later, measurements don't have to negotiate. That saves bandwidth on the back end by spending purity up front. When the environment gets noisy, coherence drains into heat. The cache invalidates. You pay with time to rebuild it. So, is this a glitch? No,
It's the opposite, a stabilizer. But stabilizers expose costs. Labs chase picosecond timing jitters because if your stamps slip, your violation dulls. Fiber losses force repeaters to stack complexity. Every quantum network is a live demo of a rule. Consistency has a cost, paid in time. And as we'll see, when ticks themselves have a price, the meter is fundamental. Time's grain, Planck limits, and discrete clocks. If consistency has a cost, maybe even a tick has a price tag. Physicists talk about Planck scales, the smallest meaningful length and time built from C, Herc, and G Planck. Time is about 5.39 times 10 to the power of negative 44 seconds. Planck length is about 1.62 times 10 to the power of negative 35 meters. Below those, our theories don't just blur, they run out of vocabulary. It's less a brick wall than a fog bank where before and after, here and there, stop behaving like separate boxes. Now, we haven't measured a discrete tick of Planck time. That would be like timing a hummingbird by watching continents drift. But the constants that define those scales are real, and the arguments that time can't be sliced finer without wrecking physics are serious. Gravity plus quantum mechanics breeds uncertainty that swallows any attempt to pin events too closely. Try to localize an interaction into a tinier and tinier spacetime cell, and you pour in energy. Pack in enough, and you create a black hole. The measurement deletes itself. Think of sampling theory. If reality has a maximum frequency of change, some ultimate pace at which states can vary, then trying to treat it as infinitely smooth risks aliasing. That's the Nyquist lesson. Sample too slowly, and fast wiggles fold into fake slow ones. Our classical intuition assumes the world's a movie shot at infinite frames per second, but every detector we build has a bandwidth. If the universe itself has one, then continuity is a reconstruction, not an axiom. So we look for seams. High-energy astrophysics is a good hunting ground. If space-time were granular, different energy photons might take slightly different times to travel cosmic distances, as if the medium had a tiny dispersion. Gamma-ray bursts, GRBs, offer a lab. They fire photons across billions of light years in a single sharp event. Telescopes like Fermi and ground-based Cherenkov arrays have combed the arrival times of low versus high-energy photons, looking for systematic delays that scale with energy. So far, the constraints are brutal. If there's grain, its imprint is smaller than we can see. No evidence of a coarse lattice that scrambles light on the way. That cuts two ways. On one hand, it protects Lorentz invariance, the symmetry that keeps the speed of light constant for all observers. On the other, it tightens the budget. If time has pixels, they're sub-pixel to our best cosmic stopwatches. Smoothness holds astonishingly well. The grain, if real, must hide behind error bars so thin they're hard to pay for experimentally. The meter exists, but it's expensive to read. Here's a human moment. A gamma-ray astronomer sits through an all-night burst alert. The trigger is strong, energy's high, timestamps crisp. They slice the light curve into microsecond bins and cross-correlate energy bands. A rumored dispersion would shift a peak by tens of microseconds over billions of years. Their plot shows nothing but statistical wiggle. Relief and disappointment collide. No easy crack, just a tighter limit. The universe declines to confess. Meanwhile, theorists sketch possibilities. Loop quantum gravity imagines weave-like structures of space-time that average to smooth geometry at large scales. Causal sets propose that events form a discrete, partially
ordered network. No background stage, just relations. These models don't predict jitter you can see today without breaking symmetries elsewhere. So the hunt shifts to subtle signatures. Polarization rotation, minute deviations in gravitational wave dispersion, or correlations in the primordial microwave sky that would hint at a granular birth. Gravitational waves become a new probe. LIGO and Virgo catch space-time ripples from merging black holes and neutron stars. If the medium had a frequency-dependent speed limit, high-frequency components of a chirp might arrive off-beat. Current bounds say the beat holds. Again, limits sharpen. Again, smoothness survives. If there's a clock under the floorboards, it's quiet, or exquisitely well-coupled so the dance we watch stays fluid. Why push so hard on grain if we keep finding smoothness? Because the budget story pushes back. A finite information universe suggests a cutoff somewhere. You can't store infinite digits of position or time in a bounded system without hiding them in redundancy. If tick size is non-zero, exact simultaneity becomes a convenience, not a fact. That would explain why every serious timing experiment leans on protocols, smearing, averaging, error correction to keep a second usable. We're fitting curves through sampled points, not tapping an ideal metronome. Here's the catch. Discreteness doesn't have to look like a blocky video game. It can be like a lossless codec,
The underlying degrees of freedom are finite, but the emergent picture is smooth until you push an extreme. The Planck fog is that extreme. Approach it with energy, you pay in heat and collapse. Approach it with precision, you pay in time and resources. Either way, the tollkeeper stands at the same bridge. Think back to entanglement as global bookkeeping. If geometry itself is stitched from patterns of correlation, then time's flow might be the rate at which consistent histories can be extended without violating those patterns. That's a mouthful, but the intuition is simple. Adding a tick means updating a lot of relationships. If each update costs, then the grain of time is set by the maximum safe update rate. Push harder and errors, noise, decoherence, glitches, rise. A micro story to end the thought. A lab attempts a quantum clock that beats with trapped ions and lasers stabilized to absurdity. They compare two identical clocks across a hallway and find agreement to 18 digits. Then they raise one by a centimeter. General relativity says time should run faster, higher up. It does, by parts in 10 to the power of 18. The hallway becomes a time gradient. That's not grain, that's curvature. But it reminds us, time is local, expensive to compare, and sensitive to context. If there's a pixel, it hides beneath layers of smoothing we built and the universe built to keep the ledger balanced. When ticks cost energy, heat shows up where logic flips. Heat of computation, Landauer in the wild. We've been circling the price of a tick. Here's the invoice in plain heat. Landauer's Principle says every time you erase one bit, force a memory from maybe to no, you dump at least kT on 2 of energy as heat into the environment. Not a metaphor. Experiments with single-molecule traps and nanoscale circuits have measured that minimum. Logic flips raise temperatures. Information has a thermal shadow. Now scale that from tabletop tricks to the places we live. A data center isn't a building, it's a climate. Racks inhale electricity and exhale heat. The hotter you run, the more errors creep. Cosmic rays, leakage currents, thermal noise, so you cool harder. Then the cooling costs power, and the power brings more heat. Engineers fight back with reversible logic demos, adiabatic clocks that try not to erase, and near-threshold computing where voltage drops so far that speed slows but energy per operation dips. It works, with caveats. Slow clocks, fragile margins, finicky designs. You save heat by trading time. Meanwhile, delete isn't free. Garbage collectors and software pause the world to reclaim memory. Microseconds in phones, seconds in servers. That pause is a heat budget in disguise. You're consolidating state, flushing caches, resetting blocks. Every reset is Landauer's fee. Write amplification in flash storage. Rewriting big chunks to change small things becomes a thermal tax you plan for with wear leveling and over-provisioning. The ledger never goes to zero. You're pushing heat around so logic can stay crisp. Labs chase the floor. Bennett and Toffoli showed that in principle, computation can be reversible. No erasures, just permutations of state. Bill Gates that scrupulously keep every input bit encoded in the outputs, and Landauer can't charge you. In practice, wires leak, transistors dissipate, and noise forces you to refresh and correct. Reversible computing prototypes exist. Ballistic transistors, adiabatic logic families, superconducting loops. But they run like a careful waltz, not a sprint. You trim heat by
surrendering throughput. That theme's familiar by now. Black holes are the universe's extreme garbage collector. Toss in messy matter. The horizon area grows to account for the new entropy. If information can't be destroyed, it has to leak back in the slowest, thinnest way possible. Hawking radiation. That build takes longer than any human story, but the sign is the same. Erasure isn't allowed without a receipt, and the receipt is heat. The information paradox sharpened this intuition. Either unitarity fails, a cardinal sin, or the radiation encodes what fell in. Holography and quantum error correction circle an answer. Information is preserved, but it takes work. Entanglement structure, redundancy, long waits to make sense of the ledger. Here's a human moment. A chip team pushes a new AI accelerator to the edge. Training runs spike temperature sensors. Throttles kick in. Error rates creep when a corner of the die runs a few degrees hot. ECCs results but adds latency. They drop clock speed 2% and cut errors by half, improving time to accuracy. The room sighs. Less heat, better answers, slower seconds. The fix isn't glamorous, it's honest physics. In another building, a quantum computing group grapples with T1 and T2 times, the lifetimes of their qubits before noise scrambles them.
Every microwave pulse that resets a qubit to zero pushes heat into the fridge. The dilution refrigerator groans at millikelvin, throwing kilowatts out the back to keep microwatts cold at the chip. Every error correction cycle multiplies resets. The machine's heartbeat is a thermal budget. Fewer erasures lengthen coherence but drag the pace. Speed up, and you buy errors you then have to erase, paying Landauer twice. Meanwhile, sensor networks and telescopes face the same math in different clothes. You can sample faster and drown storage, or you can compress on the edge and throw away possible surprises. Compression is structured erasure. You keep patterns, lose microstates. The savings convert to heat somewhere, on the device, in the base station, in the data center. Choose where to sweat.
Choose when to wait. What nobody knew at the time we first cited Landauer is how far the analogy would stretch. Every clean bit we trust in civilization, financial transactions, GPS timestamps, medical images, has an erasure trail behind it. Temporary buffers cleared, caches invalidated, logs rotated. The smoother we want our seconds, the more we reset behind the scenes to keep them monotonic. Glitch-free time is purchased by flushing ambiguity. The heat piles up out of sight. Now fold the lesson back into our budget story. If the universe runs finite memory and finite energy, it'll favor operations that avoid erasure. Global constraints that maintain coherence, reversible evolutions where possible, batching and burst release when necessary. Where it must erase, it will slow, cool, or radiate. That shows up as latency in labs, throttles in chips, millennia in black holes. Changing bits changes worlds. There's a thermal price to reality. Edge cases reveal constraints, sometimes violently. Leap seconds, GPS, and the price of precision. We've been tracking the heat bill for bits. Now watch what happens when the bill lands on a clock. GPS doesn't care about your wristwatch, it runs its own time. Each satellite carries atomic clocks steered to GPS time, a smooth scale that ignores leap seconds. Meanwhile, the world's civil time, UTC, adds leap seconds to stay in step with Earth's slowing spin. The two time streams must be reconciled in receivers, across networks, inside exchanges. Most days, it works. On leap second nights, you can hear the gears grind. Start with what GPS actually does. A phone or plane listens to multiple satellites and solves for 4 unknowns, 3 spatial coordinates and time. That last one, the receiver clock offset, is the key. If your clock is off by a microsecond, your position is off by hundreds of meters. So GPS sends time down with each signal, along with ephemerides and correction terms for relativistic effects. Yes, relativity is not optional. Satellite clocks tick differently in orbit. Ground stations discipline them. Control segments update them. The system is a ballet of corrections that assumes the second is clean and monotonic. Then the world inserts an extra tick. A leap second is announced months ahead. Operators can step it, hold 23 hours, 59 minutes, and 60 seconds for 1 second, or smear it, stretch a day so the extra second is spread thin across hours. Different stacks choose differently. If one service smears and another steps, their logs disagree for a whole day by fractions large enough to break strict ordering. Distributed systems that assume time never goes backward may see a duplicate timestamp and spin. We've seen it. Databases that double insert kernel timekeeping bugs that deadlock, schedulers that reschedule everything at once. Here's a micro story. A trading firm in Chicago thinks it's ready for a leap second. Their time source smears, a counterparty source steps. For one intense minute, orders arrive stamped slightly in the future relative to the local clock. The matching engine rejects some, flags others for review. Latency-sensitive strategies drift. Nothing illegal happens, the P&L still stings. Afterward, the postmortem reads like a weather report. Pressure fronts of time from different suppliers colliding over an exchange. The fix is policy, mandate a common approach, and hardware. Discipline clocks harder. The cost is real. Redundant timing links, holdover oscillators, better monitoring. More power, more heat. Meanwhile, power grids live and die on phase, which is just time in a sinusoid. A generator must match grid frequency within tight tolerances or it trips. Synchrophasor networks sample voltage and current tens of times per cycle and tag each sample with GPS-disciplined timestamps. A handful of microseconds matter when you're triangulating a disturbance across states. Now throw in a leap second mishandled by one vendor's firmware. Suddenly, some phasors slide out of phase on paper while the physics stays in step.
Operators chase a ghost fault while alarms squawk. The grid holds, but the night is long. A second case. A major web service experiences a leap-second night where a kernel bug spins CPU cores to 100% when the system clock repeats a timestamp. The machines don't crash, they just stop doing useful work. Engineers drain traffic, reboot fleets, apply patches. The lesson isn't glamour. It's that time lives in every layer. Kernel, JVM, database, cache, load balancer. Each layer interprets the tick. Each can panic at a duplicate. GPS looks smooth because it refuses to acknowledge leap seconds at all. UTC lurches to keep faith with the sun. Receivers reconcile them with offset tables. Miss an update and your device thinks the world jumped. That's happened in fleets of embedded devices, routers, trackers that didn't ingest the leap second bulletin in time. For hours, their logs drifted, their security tokens expired, and their audit trails broke. Nobody saw the extra second. They paid for it afterward in human hours. Finance makes the stakes public. Exchanges stamp trades to nanoseconds and fight over who saw what when. Microwave relays arc between cities because fiber is slower. Firms buy atomic clocks for co-location racks and discipline them with GPS, then hedge with ELORN or Common View satellites in case GPS is jammed. When a satellite's clock glitches, and it has, receivers that trusted it too much jitter. Filters help, but filters cost time. You average longer to avoid chasing noise, and in those extra microseconds, someone else wins the race. Now ground the theme. We want a perfect shared second because our networks, markets, and grids are distributed computers. Consensus needs order. Order needs time. But time is messy in practice. Leap seconds, relativity, ionospheric delays, firmware quirks, human procedures. We smooth, smear, discipline, and vote. Every fix is computation and energy. The smoother we demand the second, the more.
Overhead we carry to keep it from tearing. What nobody knew at the time we first synchronized clocks by radio is how tight this would get. We've squeezed tolerance until even a 1-second policy decision ripples into outages. When leap seconds are paused or retired, a live discussion, it won't be because the sun changed. It'll be because our stacks can't afford the jerk. The price of precision is paid upfront in hardware and policy, and nightly in watts. If civilization buckles at an extra second, what happens when space-time itself tightens the budget? Now pull back. If civilization buckles at a second, what about space-time? Missing mass, missing meaning. Pull the camera to the dark. Galaxies spin too fast for the stars we can count. Their disks should fly apart, but they don't. Something unseen is holding them together. Call it dark matter for now, a placeholder for mass that doesn't glow. Vera Rubin watched rotation curves flatten where Newtonian expectations would drop. The plot lines refused to bend without adding invisible weight. Then lensing drew the outline. Light from distant galaxies bends around massive clusters, mapping gravity's hand without caring what makes it. The bullet cluster sharpened the picture. Ordinary gas from two colliding clusters slams, heats, and lags. The gravitational mass traced by lensing sails ahead with the galaxies. Whatever makes most of the mass doesn't collide like gas, it passes through. That separation is a fingerprint, not a rumor. Zoom even further back. The cosmic microwave background encodes tiny ripples whose pattern depends on how much stuff, how much radiation, and how tightly gravity could pull at recombination. Fit those acoustic peaks and you get a recipe. About 5 times more dark matter than ordinary matter. Independent lines, rotation, lensing, CMB converge on a heavy ledger entry we still can't hold in a bottle. WIMPs, axions, sterile neutrinos. Candidates parade through detectors and colliders. So far, no handshake. Here's why it fits our budget story. Dark matter acts like scaffolding. Cheap to move, non-dissipative, able to hold large-scale structure without spending energy on radiation. It's a way for the universe to assemble galaxies efficiently. Let baryons cool into the wells later. Let the invisible mass do the quiet, heavy lifting. You can call that padding if you're feeling cute, but the physics is stern. Whatever it is, it saves bookkeeping by being simple. Cold, collisionless, abundant. Now flip the sign. In the late 1990s, supernova surveys discovered that expansion isn't just coasting, it's accelerating. Dark energy entered the ledger as a pressure with the wrong sign. Negative, driving space to expand faster.
The simplest version is a cosmological constant, lambda, a fixed energy density for empty space. Plug it into Einstein's equations and the math behaves. Live with it, and 70% of the universe turns into a uniform pressure field that dilutes weirdly. It doesn't. It stays constant as space grows. The stakes aren't just philosophical. Acceleration sets our future horizon. Distant galaxies slip away beyond reach, their light redshifting into silence. Structure growth slows. The cosmic web freezes. The age we infer depends on how lambda and matter share the budget. Change the balance and the timeline rewrites itself. Physicists tried to compute lambda from quantum field theory, summed the zero-point energies of modes up to some cutoff, and got a catastrophe. A value absurdly larger than observed. Tweak the cutoff, it's still off by orders of magnitude. That mismatch is famous because it's so bad. You can read it as an accounting error, or as a hint that empty space is balanced to a precision that begs for mechanism. Or you accept lambda as a parameter you measure and move on, a constant you rent, because owning it wrecks your books. Meanwhile, alternatives whisper from the margins. Maybe gravity itself bends differently on large scales, modified dynamics that flatten rotation curves without dark matter. Muon and its relativistic cousins can mimic some galaxy behavior with fewer assumptions, but they strain at clusters and the CMB. They pay a price somewhere else. The pattern repeats, trade-offs and seams. Fix one dataset, tear another. Here's a micro story. A theorist stares at a whiteboard packed with halos and transfer functions. She toggles a parameter in a simulation, boosting feedback from star formation so baryons blow out of dwarf galaxies. And the observed satellite galaxy count matches beautifully. But a different plot sours. The inner density profiles look too chord. She dials back. The match migrates. The intuition lands. Dark matter might be simple. Baryons are messy. You spend precision fitting the messy part, not the dark scaffold. In another building, an axion search cools a cavity to near zero and tunes a magnetic field, listening for a whisper of microwave photons that would signal a conversion. Days hum by. Peaks rise from noise and
fall again under scrutiny. Progress is measured in exclusion plots. Regions of mass coupling space turn from maybe to no. Every no is information paid for with time, power, and patience. Why call the dark sector padding without sliding into fantasy? Because if the universe has a finite information budget, smooth global behavior might be enforced by fields that act like invisible accountants. Dark matter carries structure without friction, keeping orbits tame. Dark energy smooths curvature on the largest scales, stabilizing expansion with a simple rule: constant density per unit volume. You don't need intention, you need economy. Two coarse fields that do heavy work with minimal adjustable knobs. But there's a bill. If 95% of the ledger lives in entries we don't see, our meaning-making leans on a slim slice of reality. Our models are strong because they predict and cross-check, not because we name the unknowns. The names are placeholders. The strength is in how the placeholders stitch multiple phenomena into one fabric without tearing others. That stitching is the hard part, and it's where budgets show. What nobody knew at first was how much dark energy would shape our urgency. Surveys now race to map baryon acoustic oscillations, weak lensing shears, and redshift space distortions with ridiculous precision to pin west as close to -1 as possible, or find its drift. Each decimal narrows theories and raises the cost of consistency elsewhere. Instrumental systematics become as treacherous as theory priors. It's a duel fought in petabytes and calibration lamps. Read the dark sector with the thread we've built. When a system is resource limited, it offloads complexity into regular fields and simple scaffolds. You can't resolve every star's path everywhere, so you encode gravity in a smooth potential. You can't carry infinite microstates, so you let expansion dilute detail and leave a low parameter residue that holds the shape together. That's not simulation talk. It's thermodynamics of description. The human feeling, though, is straightforward. Most of the universe is a balance sheet entry we can't directly touch. We infer it by how it keeps time for galaxies and how it paces expansion. If that's the cost of a stable, large-scale cosmos, we're lucky the fee is regular. If the fee fluctuates, everything we trust, ages, distances, fates, drifts, nature hides detail, maybe on purpose. Holography, error correction, and protected reality. We've been circling the budget, finite bits, heat for erasure, global consistency. Now step into a framework that makes those instincts concrete. Holography says a region's physics can be fully described by data living on its boundary, with no more information than the surface can hold. It isn't a parlor trick, it's a survival rule.
Store only what you must, protect it with redundancy, and let geometry emerge from relationships. The seed was black hole thermodynamics. Entropy scales with area, not volume. The holographic principle pushes that logic outward. If a black hole's microstates sit on its horizon, maybe every patch of spacetime has a boundary bookkeeping that's sufficient to recover the interior. Yada's CFT made that audacious idea tangible. A quantum field theory without gravity, defined on a boundary, encodes a gravitational bulk inside. Two very different descriptions. One, physics. Change the boundary state. The interior geometry reshapes. Space as it appears is a compression of a deeper, lower dimensional ledger. Here's where error correction walks onto the stage. In toy models, tensor networks like Mera, Happy Codes, you can literally build a bulk from a boundary code that corrects errors. Lose some boundary qubits to noise and you still reconstruct the interior state. The redundancy is structured. Local erasures don't kill global meaning. That looks like a blueprint for protected reality. The universe uses code-like redundancy, so the interior, the stuff we live in, survives scratches on the boundary. A human moment. A whiteboard crammed with tensors, arrows, and loops. A small group iterates a mapping from boundary logical qubits to bulk degrees of freedom, arguing over which pattern of erasures the map can tolerate. Someone nudges a tensor. The network regains the ability to reconstruct a particular bulk operator even if a boundary wedge is missing. There's a quiet satisfaction. They've built a little universe that forgives. Meanwhile, Ryu Takayanagi ties entanglement to geometry. The area of a minimal surface in the bulk computes entanglement entropy on the boundary. Translate that. How much two regions share in bits sets the size of a geometric cut between them. Entanglement is scaffolding. Vary the correlations, the distance flexes. That's economy in action. Geometry is not stored twice. Once as distances, once as correlations. It's stored once as correlations. Fewer moving parts, fewer bits, less heat. Now add dynamics. The holographic dictionary is thick.
But its theme is clean, robust features of the bulk, horizons, causal order, even black hole interiors, mapped to error-protected subspaces on the boundary. Protected doesn't mean infinite capacity. It means tolerant of local faults. That lines up with our lived world. Local glitches, cosmic ray flips, clock hiccups, rarely demolish global laws. Conservation, causality, gauge invariance feel like checksums. What nobody knew early on was how far the code metaphor would reach. Page curves, plots of how entropy and Hawking radiation evolves, once looked like an indictment of unitarity. Holography and replica wormhole calculations now suggest that late-time radiation purifies, as if the code scrubs and recombines information that initially looked lost. The ledger balances, but only after an extended audit. That's error correction with a latency you can measure in cosmic patience. Here's a micro-story. Two theorists compare a simple holographic code to a noisy channel. They flip random boundary bits and watch which bulk operators become unrecoverable. The failures cluster at the edges of the reconstructible wedge. The entanglement wedge shrinks first at the margins. They underline it. Codes fail first at the edges. Then they pull a news report about a regional power disturbance that started in the periphery of a grid and cascaded inward. The analogy isn't proof. It's a model that hums the same tune. Stress eats protection from the boundaries in. On the lab side, quantum error correction is a grind. Surface codes spread a logical qubit across many physical qubits, measuring stabilizers to catch flips without reading the message. Every cycle is a bet. You trade extra hardware and time for resilience. Fault tolerance arrives when error rates drop below a threshold and the code's overhead pays off. That threshold is a knife edge. Too noisy and your corrections create more errors than they remove. Quiet enough and logical lifetimes grow exponentially with code size .binning. Protected reality feels like running under threshold. Impact lands in two places. First, interpretation. If space-time is an error-corrected code, then laws are properties of the protected subspace, not fragile accidents. Violations would appear as rare logical faults when budgets tighten, edges fraying, symmetries wobbling at extremes. Second, practice. Building quantum computers has trained a generation to think in stabilizers, syndromes, and thresholds. That vocabulary feeds back into how we picture the universe guarding its own consistency. Keep us honest. Ada's CFT lives in a negatively curved toy universe, not our de Sitter expansion. The code models are sketches, not blueprints. But they've earned respect by predicting patterns, like how entanglement rearrangements reshape the dual geometry that match exact calculations. They teach a habit:
Whenever a description survives noise, look for redundancy and a decoding map. Now fold it into the budget narrative. A finite information universe needs protection to avoid spending heat forever chasing local errors. The cheapest protection is structure, constraints, symmetries, redundancy. Holography supplies a map where those features aren't optional. They're the only way an interior can exist with fewer boundary bits than naive volume counting would demand. Error correction explains why small glitches don't metastasize while leaving room for rare, costly failures at the fringes. And there's a warning nested inside the elegance. Codes protect up to capacity. Beyond that, errors percolate and logical information melts. If reality is protected by entanglement structure, then places where entanglement thins, cosmic horizons, ultra-high energies, the earliest times, are where the guardrail flexes. We wouldn't see cartoon artifacts. We'd see seams, parameters that refuse to harmonize, clocks that won't quite agree, symmetries probed to the brink. The budget is finite, the code is strong, the edges still matter. Edge failures, UHEKers, GZK cutoff, and high-end limits. Fence posts aren't the crisis, the stampede is. Start at the highest energies nature throws at us. Ultra, high-energy cosmic rays, protons, or nuclei accelerated to energies above 10 to the power of 19 electron volts, sometimes brushing 10 to the power of 20. One of these particles can carry the kinetic energy of a major league pitch packed into a single proton. They arrive rarely, 1 per square kilometer per century at the top end, yet they write in capital letters about the limits of our laws. Here's the scene we watch. The Greisen-Zetsepin Kuzmin cutoff. Above roughly 5 times 10 to the power of 19 eV, protons smashing through the cosmic microwave background should lose energy by producing pions. Space becomes a thin molasses. Over tens of megaparsecs, the highest energy travelers should be tamed, shaving the spectrum's tail. That prediction isn't a quirk. It's basic kinematics plus the CMB we've mapped to exquisite precision. If you see lots of events far above the cutoff from all directions, something's off. Either the
Primaries aren't protons, the sources are close, or our understanding of interactions or backgrounds misses a page. Action looks like showers in the atmosphere. When a UHEKar slams into air, it triggers a cascade. Billions of secondary particles fanning out. Arrays like the Pierre Auger Observatory spread detectors across the pampas to catch the deluge, while fluorescence telescopes watch the sky glow as nitrogen recoils. From timing, footprint, and light profiles, teams infer the primary's energy, and sometimes its mass. Early hints decades ago suggested events above the GZK limit. Later, larger datasets saw the spectrum steepen, consistent with the cutoff. Relief. But the details won't sit still. Composition seems to change with energy, nudging heavier at the top, and isotropies whisper of source regions near the local supercluster. Correlations wobble as data grows. Here's why it matters for budgets. The GZK effect is a high-end rate limiter. It says, beyond this energy, the universe charges a toll proportional to distance and composition. That toll is paid in pions, neutrinos, and photons, debris that then becomes another channel to check. If the ledger holds, cosmogenic neutrinos should trickle to our detectors, a faint confirmation that the cutoff is doing its work. Ask IceCube and radio arrays listening for Ascarian flashes in polar ice. So far, limits tighten, candidates tease, and the parameter space for sources narrows. The budget asserts itself with scarcity. Meanwhile, symmetries get stress-tested. Lorentz invariance, our bedrock that keeps physics the same in all inertial frames, would crack dramatically if dispersion relations tweaked at extreme energies. Woka, air showers, TeV, gamma rays, and polarized light from distant sources probe for birefringence, energy-dependent speeds, or threshold shifts in particle decays. The story so far, no convincing cracks. Constraints bite hard. If space-time has grain or preferred frames, their imprint hides below our current floor. That's protection working at the edges, not failing. A micro story. A night at Auger ends with a candidate at the high end of the spectrum. The surface station's timestamps line up, the fluorescence profile is clean, and the reconstruction nails a direction skimming near a known active galaxy in the local universe. The team checks weather, calibration lamps, atmospheric clarity. The energy scales down a hair after a cross-check. It still lands in the tail. The map gets one more pin. It doesn't scream new physics. It whispers. Your sources are near, your cutoff holds, your world is tight. Now pivot to composition. If the top end leans heavy, iron nuclei instead of protons, the GZK story mutates.
Photodisintegration off the CMB and infrared backgrounds strips nucleons, dropping energy in steps and seeding secondaries differently. Shower maxima, where the cascade peaks shift accordingly. Experiments disagree softly across energies about just how heavy the tail is. Systematics, hadronic interaction models extrapolated far beyond collider energies, sneak in. That's another edge. We simulate air shower cores with physics we haven't directly tested. LHC data helps calibrate. Above that, we infer. The budget shows up as uncertainty we can't cheaply erase. Parallel checks keep pressure on the fence. TEV, PLV gamma-ray telescopes chase spectral cutoffs and pair production horizons on extragalactic background light. If high-energy photons arrive from farther than they should without attenuation, something's amiss. Either the background is thinner, or photons convert to axion-like states and back, or Lorentz symmetry flexes. So far, attenuation looks normal, with interesting exceptions being fought over with better calibrations. Again, edges flex, guards hold. Impact lands in a pattern we recognize. At the highest energies and longest baselines, nature plants limiters, energy loss processes, interaction thresholds, symmetry checks that act like circuit breakers. They don't scream simulation, they enforce budgets. Push a proton too hard, the CMB taxes it. Aim photons across the cosmos, backgrounds consume them. Try to tilt symmetries, precision snaps them back. We learn because rare violations would blaze. Instead, we get fences where we expect them, and stamps of nearby sources peeking over. What nobody knew at first was how informative a steepening could be. The cutoff wasn't an ending, it was a pivot to multi-messenger accounting. If Yuki cars bleed energy into pions, then neutrinos and gamma rays carry receipts. If sources are local, catalogs of active galaxies and starburst regions become suspect lists. Every null detection tightens the web. The lesson repeats. The edges don't fail loudly. They ration, they redirect. They remind us the universe has high-end limits, not as a tease, but as a way to keep the ledger stable when the stampede hits.
Cascades, when small glitches avalanche. We've watched fences hold at the edges. Now walk into places where the problem isn't a fence, it's the crowd. Complex systems look stable right up to the second they don't. A power grid hums until a branch kisses a line. A market trades until a timestamp jitters. A software stack serves until a rare state collides with a maintenance window. The failures aren't exotic. They're ordinary events that line up in just the wrong order, and then everything moves at once. Start with a grid, because grids speak in time. Frequency is a shared heartbeat. Every generator listens to the same beat and pushes on the same curve. A tree takes out a line in hot weather. Load reroutes, another line sags and trips. Protective relays do their job, and quickly the job becomes too big. Frequency dips. Inertia buys a breath, then automated shedding lops off neighborhoods to save the spine. Sometimes it works, sometimes it doesn't. In the 2003 Northeast blackout, alarms flooded operators, SCADA screens lagged, and a handful of minutes separated a contained incident from a cascade that rolled across states. Nobody decided to turn off the lights. The sequence decided. The stakes are visceral. Hospitals switch to generators. Water plants coast on stored pressure. Phones choke. The cost is measured in lost work, spoiled inventories, and the quiet horror of a city without elevators. The fix, years later, reads like a checklist of timing discipline. Better state estimation, phaser measurements with tight GPS stamps, automated islanding policies that carve grids into self-sustaining blocks when the big machine starts to fall out of step. You pay in hardware, in redundancy, in training. You pay to keep the second tame. Markets cascade differently, but rhyme. A fund sees a price flicker, a model triggers, liquidity thins, and algorithms withdraw to watch. That withdrawal becomes the event. Liquidity spirals while timestamps try to impose order on trades arriving across microwave links and fiber. A flash crash doesn't need fraud, it needs feedback, and a shared strategy that reacts faster than humans can moderate. Afterward, rules arrive. Circuit breakers, limit up, limit down, dark pool transparency. You widen the guardrails and accept a slower, safer beat when the air gets thin. Software is a lab for cascades we can watch in logs. A microservice times out, retries fan out, load balancers think they see a healthy node and stuff it, caches grow stale, and suddenly, a trivial dependency outage becomes a full-site event. Chaos engineering turns this into practice. You pull plugs on purpose, measure blast radius, teach teams to see how fast an ordinary glitch can avalanche. The lesson keeps repeating. Coupled systems turn local surprises into global problems if they share a clock and a goal. Here's the math mind hiding underneath.
Self-organized criticality paints a picture of systems tuned by slow inputs and fast releases, sand piles fed grain by grain until a single grain causes a slide. Most slides are small, a few span the whole slope. Earthquakes, avalanches, network outages, market moves. Their sizes often follow power law distributions. You can regulate, you can damp some channels, but you can't make the pile forget gravity. That's not a failure of design. It's a property of being connected under load. A human moment makes it plain. A grid operator watches frequency drift below nominal, a dull ache of alarms rising in the control room. They have 30 seconds to decide whether to shed a big industrial feeder. The phone lines light up, nobody wants to be cut. In those stretched seconds, time feels thick. They shed. A minute later, frequency recovers. Later, they learn another region tripped anyway. The cascade splashed their boundary and receded. Their choice mattered. It wasn't sovereign. It was one gate in a river. Parallel that with a site reliability engineer staring at a dashboard where latency spikes pan across services like a storm front. They have retry rates, switch from exponential backoff to jittered caps, and watch a curve flatten. Somewhere else, a team restarts a fleet to roll a bad config. The roll triggers a cold cache thundering herd. For a few minutes, everything that depends on those caches feels slow. The incident review the next day reads like choreography, small errors, near misses, fortunate buffers. Nobody planned the dance. Everyone danced. So what does this have to do with time breaking down? Cascades are what budgets look like when local fixes get cheap and global slack gets expensive. As we squeeze tolerance, demanding tighter timing in finance, thinner margins in grids, lower latency in networks, we saw fat trimmed from everywhere that isn't the fast path. Redundancy becomes dynamic. Inventory becomes just in time. Under normal load, it's efficient. Buffers shrink. Under stress, there's nowhere for uncertainty to go but through. Read the physics in the same light, those seams.
At extreme energies and long baselines aren't catastrophes. They're limiters that keep cascades from running away in the laws themselves. But if the underlying ledger has less slack, if finite information and energy budgets tighten, then reconciliation events have to be bigger or more frequent. That shows up first where coordination is hardest. Across space, across scales, across instruments and institutions, bound to a shared second. What nobody knew when we fell in love with optimization is how much it steals from resilience. The savings are real until they aren't. A smooth, thinly buffered world is fast and brittle. A world with slack is slower and forgiving. The programmer's dilemma we saw in chips and telescopes plays out in civilization. Throughput versus fidelity. Every time we push for more throughput, we rely on error correction to save us when a grain slips wrong. Most days the code holds. Some days the pile moves, the warning isn't mystical, it's practical. If our seconds are under pressure, local glitches will seek global paths. The events we call once in a century could cluster. Not because the rules changed wildly, but because the buffers did. The stampede is load, not malice. The fix is the same across domains. Add slack, add sensing, slow a little, correct early. Or keep shaving margins and accept that when pressure keeps rising, something has to give way first. The time ration, why every second feels shorter. We've watched systems ration bandwidth, energy, and precision. Now feel the ration land inside your head. Subjective time isn't a clock, it's a construction. Your brain predicts what's next and updates when it's wrong. Novelty forces updates, repetition lets you skip. Childhood stretches because everything is new and errors are frequent. Adulthood compresses because the model's good and the surprises are small. The day is dense in motion, thin in memory. Predictive coding is the blueprint. Sensory cortex runs a loop. Top-down guesses meet bottom-up signals. Mismatches flag error to fix. Fewer mismatches, fewer updates, fewer memorable frames. You aren't living faster. You're storing less about each unit of external time. The experience of speed is compression. Hours collapse in recall because the brain saved a summary instead of the footage. That's efficiency in action, an internal error-correcting code keeping the narrative smooth by throwing away microstates. Stress distorts the loop. When threat is high, attention narrows, arousal spikes, and time seems to dilate. The brain oversamples salient cues and writes more frames per second to memory. Later, those packed frames replay as slow motion. In experiments, participants exposed to danger overestimate durations. In labs, saccades, heartbeats, and oscillations shift phase under load. Your internal metronome is elastic because the budget is adaptive. Spend on detail when survival is on the line, save when it isn't. Now add culture as a clock. Always-on networks flatten the world into a single hyperactive timeline. Messages expect immediate replies.
feeds never end. Work creeps into weekends, entertainment algorithms remove friction between episodes. Latency intolerance, our inability to tolerate waiting, tightens everywhere. A loading spinner that used to be fine now feels like failure. We're engineering out idle time, the blank spaces that once let the mind re-index. As buffers vanish, days feel packed and oddly forgettable. The second is engineered to be full and ends up empty in hindsight. Here's a micro story. A hospital resident finishes a shift, badge pings, pager pings, EMR alerts stack, and breaks become micro scrolls of headlines. 12 hours pass inside a pinball machine of alarms and tiny decisions. On the subway home, the resident tries to recall lunch. There's a receipt, not a memory. The day was real and useful. It's sparse in recall because the model ran on defaults, the anomalies were small, and the attention budget was spent on triage, not on writing new chapters. Meanwhile, our instruments teach us the same rationing. To save power, phones drop screen refresh rates when content is static. Browsers schedule repaints only when layout changes. Video codecs predict most frames and only transmit differences. Life online is motion predicted, with corrections spliced in. It feels smooth because the human visual system plays along. Your brain is the decoder, well-tuned to accept interpolation as reality. The saved cycles show up as battery life. The cost is subtle. Fewer cues anchor time in memory. The physics thread we've pulled through the story shows up here too. If the universe pays for erasure with heat and pays for consistency with preparation, then change is expensive and stasis is cheap. A world under budget pressure will prefer routines, correlations, and cached paths. Your mind, embedded in that world, inherits the same economy. Reuse patterns, compress experience, and flag only high-value mismatches. As novelty
Declines with age, the compressor grows bolder. The perceived year shrinks. Social acceleration compounds it. Logistics shave days. Streams drop whole seasons. Markets move in microseconds. Emails fill minutes that used to be quiet. We align to external clocks that march faster than human rhythms, and then we add more clocks. Fitness trackers, productivity dashboards, sleep apps. Each adds feedback, and feedback adds work. The metric becomes the mission. The day becomes a ladder of micro deadlines. The subjective second thins because it's packed with obligations that don't write distinct memories. What nobody knew at the time, we call time perception psychology, is how tightly it couples to information flow. Block notifications for a week and hours thicken. Move to a new city and months expand. Take up a skill that defeats your priors and the clock loosens. That's not mystical. It's budget allocation. The system spends more bits per moment when prediction fails gracefully and pulls back when prediction wins. The edge case reveals the rule. In boredom, minutes drag and vanish in recall. In flow, clear goals, immediate feedback, just beyond skill challenges. Minutes vanish and return as rich memory. Flow spends the budget well. Heightened attention without panic, novelty without chaos, error signals that guide improvement. It's a reversible computation of sorts. Minimal erasure, maximal reuse, low heat. The hour feels short, but counts long afterward. Read it with our larger thesis. If there's a finite cosmic budget, and if our civilization pulls buffers tight, our minds will feel the squeeze first. Subjective time red lines before atomic clocks do. The fix rhymes across scales. Add slack, reintroduce novelty, slow some loops, protect attention with boundaries, and accept that fidelity costs throughput. The second we live is a ration, and we choose how to spend it. Reversible worlds, running the tape backwards. We've been living with a trade. More certainty means more heat, but there's a loophole that's less magic and more discipline. What if you don't erase? What if you compute in a way that keeps every bit of the past encoded in the present, so there's nothing to pay? That was the audacious point Charles Bennett made in the 1970s, extending Rolf Landauer's insight. Erase your costs, but logic itself doesn't have to. Edward Fredkin and Tommaso Toffoli built it out in gates, reversible gates, where inputs can be recovered perfectly from outputs. In principle, you can run the tape forward, then run it backward, with no heat bill at the gate level. In practice, we leak. Real devices have resistance, wires have capacitance, and noise drifts in. But the blueprint stands. If you preserve information at every step, you owe Landauer nothing. Reversible computing tries to live in that blueprint. Adiabatic logic charges and discharges slowly, so energy sloshes rather than sprays. Ballistic devices let signals coast in near frictionless channels. The cost is speed. You move gently, you safeguard state,
and you accept that your clock ticks fewer times per second because each tick is careful. Here's what that looks like on a bench. A grad student tunes a reversible adiabatic circuit that adds 2 numbers without clobbering intermediate bits. The power rails aren't square. They're smooth ramps that hand energy back to the source on the downstroke. Oscilloscopes show little sips of current instead of gulps. It works until a small timing skew stacks up and a latch slips. Debugging means tracing information threads through the circuit and making sure none got quietly erased. The fix isn't to add a reset. That would be easy and hot. The fix is to slow a phase, realign, and keep every breadcrumb. Physics has its own version of running the tape back. The microscopic laws, Schrodinger's equation in quantum mechanics, Hamiltonian flow in classical mechanics are reversible. If you know the full state exactly, you can compute forward or backward. But we rarely know the full state, and we couple to environments that act like shredders. The Loschmidt echo is a lab's way of testing reversibility. Evolve a quantum system forward for a while, then try to invert the dynamics and watch the state return to its origin. In small, well-isolated systems, you can see the echo. As complexity rises, tiny errors amplify, and the echo fades. Reversibility fails not because the laws changed, but because noise and chaos ate the breadcrumbs faster than you could keep them. Spin echoes tell the same story in NMR. Dephase a swarm of nuclear spins, flip them with a pulse, and they refocus. Their lost order returns, like footsteps retraced. That trick works because you designed the disturbance and its inverse. Try it in a crowded, messy world, and stray couplings smear the path. You can rewind only what you protected. A human moment makes it plain. A quantum lab runs a many-qubit circuit and attempts an echo. Forward with a messy Hamiltonian, then backward with its
Negative. After the turn, the measured overlap with the initial state climbs, peaks below perfection, then decays. They push harder, better calibration, stronger error mitigation, and the peak rises a bit. Every extra percent costs more time and more care. The lesson lands. The arrow of time we feel isn't a law. It's an accumulation of tiny losses we don't pay to avoid. Reversible logic reaches into algorithms too. Bennett showed you can make any computation reversible by storing intermediate results and then uncomputing them, running subroutines backward to clean up garbage bits. That's the tidy way to finish a calculation without erasure. Compute answer, copy the answer to a safe place, then run the steps in reverse to restore the machine to its original state, leaving only the answer. Elegant, but memory hungry. You trade time and space to dodge heat. Quantum computing bakes this in. Unitaries are reversible by definition. You never throw information away inside the algorithm, but you pay at the edges. Measurements are erasures that dump heat into the fridge, and error correction, crucial to keep coherence, relies on resets. Quantum advantage lives in the reversible heart, while the boundaries collect the bill. Engineers squeeze those boundaries, moving more of the task into clean unitary blocks and staging fewer, smarter measurements. They're trying to spend less heat per insight, and they buy that with latency and architecture. Now widen the lens. If our universe prefers reversible evolution, conserving information in the global wave function, then it has a bias. Reuse rather than delete, rearrange rather than reset. You can feel that in places where dissipation is low and dynamics are coherent, superfluids that flow without friction, superconductors that carry current forever, planetary orbits that track predictable ellipses for ages. Order persists when the environment can't steal it easily. Reversibility isn't everywhere, but when conditions allow it, it saves the budget. There's a catch. Reversibility piles up history. If you keep every intermediate bit so you can uncompute it later, you carry baggage. You either store it physically, more memory, or you take the long way home by carefully winding the circuit backward. Both cost time. The reversible world is thrifty with heat and greedy with seconds. That's our thread. To avoid paying with energy, you pay with delay. Microstory. A prototype reversible processor executes a toy workload at kilohertz rates while consuming microwatts. Absurdly efficient, painfully slow. Next door, a standard chip blasts through the same work 1,000,000 times faster and warms your palm. The team demos both to a funder. The reversible chip wins admiration for its grace and loses the race for practical deployment today. The pitch pivots. Pair it with conventional logic as a low-heat coprocessor for long-running background tasks where speed isn't king. The future arrives sideways. The compromise obvious: run hot when you must, run reversible when you can. Run the tape backward in your head once more. The Loschmidt paradox asks why we see irreversible phenomena if the underlying laws are reversible.
Boltzmann's answer was probability and ignorance. There are more disordered states than ordered ones, and tiny uncertainties blow up under dynamics. Reversible computing tries to live in the narrow path where you don't let uncertainty in. Holography and error correction showed how structure can protect meaning, despite noise. The bridge is this. When budgets tighten, the only way to keep the ledger honest is to erase less and prepare more. That means more reversible moves, more caching of history, more patience. So yes, there's an escape hatch from heat. Don't delete. But it's not free. The price shows up in the tick. You slow to keep fidelity. You widen pulses, you add checkpoints, you uncompute garbage. The second stretches. If reality is leaning into reversible tricks at scale, then the feeling that time thins while the machinery labors might be the signature. There's one problem, and it's the one we've been circling since we met the bill. Reversibility costs time.